Hello, welcome to Basics of Noise and its Measurement. Today is the start of the 5th week of this course, and over last 4 weeks we have dealt with a series of topics, and particularly in the last week we had learned lots of stuff about microphones, their classification, different categories, what is the sensitivity of a microphone, what are different criteria using which we can select a microphone which meets our needs, directivity, and so on and so forth. And what we will discuss today is how to analyze sound. And we will start from a theoretical standpoint, and next week we will actually start analyzing sound. Because what happens is that you have microphone, it gives you data, and essentially what you get is some sort of a function, voltage as a function of time. And then the question is that once you have this data, voltage as a function of time, what do you do with it? How do you analyze it? So it's important to have some grounding in some of the important techniques and methods which are used to analyze these sound signals. Specifically, what we will cover today are 3 concepts. The first is what is a Fourier series expansion of a function. Then we will progress on to talk about Fourier integrals, and then we will finally close today's discussion with Fourier transform. So a lot of the material which we will cover today will be conceptual and somewhat theoretical in nature, but next week when we discuss this further, you will realize the importance of these concepts. So that's how we are going to proceed. So in this particular class we will discuss Fourier series expansions of some nice periodic functions. So we will discuss Fourier series. Okay. So the context is that suppose you have a periodic function. So let's say this my x-axis, and here instead of x I will call it, let's say, time, and on the y-axis I have some function this of time ft. An example of this function could be the sound which I am recording through a microphone, or the voltage which is being generated by some instrument, or whatever. Now this function could be a periodic function. For instance, this is a periodic function, or it could be a non-periodic function. So example of non-periodic function will be this. There is no repetitiveness in this function. So this whole concept of Fourier series is applicable to this class of functions which are periodic functions. Fourier series is not applicable to non-periodic functions. And the time after which the function repeats itself, that duration, so this function repeats itself after so much of duration, this is known as time period, or capital T. In some literature you will also find it as P, which is the period of repetitiveness. Okay. Before we go further into it, you would wonder why, what is it that we are trying to do in this. So what we are trying to do is that we are trying to express ft as a sum of sine and cosine functions. That is our fundamental goal, that if we have a periodic function, can I express it as a sum of sine and cosine functions? question will be why are we interested in doing that? So to address that, I'll give you perspective. So suppose I have a microphone, okay, and it's recording sound, and it is positioned in a room, and let's say there is one instrument, and this instrument is generating a 50 hertz tone. So this is just one example I'm talking about. So what will be, so this is some instrument, instrument A. So this is some instrument and it is generating a 50 hertz tone, and let's say it's a nice sinusoidal tone. So this microphone is receiving signals from this instrument. There could be another instrument, and what this instrument is doing is it's generating some other repeating thing, and what it is doing is that, so this is another instrument, instrument B, and for purpose of simplicity, let's say that it is generating, so this also generates some noise, and for purposes of simplicity it is generating a 60 hertz tone. So this one is doing 50 hertz and this guy is doing 60 hertz, okay, and using this microphone I am also recording this noise. So I am recording both these noise. Now there could be an interest, so what I will record will be a sum of this sound and this sound. If I plot these on a XY graph, then what the microphone is going to record is a sum of those two graphs, and that also will be repetitive. That also will be repetitive, and I may be interested in figuring out that what is the nature of this noise, and suppose this is a black box, you know, this whole thing is a black box, so I do not know what is happening in the room, but all I am recording is this thing, and I have some knowledge that okay, maybe one instrument is doing one tone and another instrument is doing one tone. If I can do a Fourier analysis of my signal, then I can resolve the signal which is recorded by microphone into its components, and then I can map these components to the specific instrument or their specific sources. So this is one motivation, that is one practical application. Why is Fourier series and some other similar representations of time signal in frequency domain important? So I can resolve a signal into individual harmonic components. This is one benefit I can have. And then if I have a physical system which is generating a lot of noise and different parts of that system are generating different types of noise, I can relate these individual harmonics to specific features of the overall system. So that is one benefit which I get out of it. So I'll draw another periodic function. So this is another periodic function, it's a sinusoidal function. The one which I had drawn earlier, this is a square wave type of a function, okay. Another periodic function could be something like this. So the point what I am trying to make is that a periodic function need not be only sinusoidal in nature. As long as a function repeats itself, it is a periodic function. Sinusoidal functions are a particular type of periodic functions, but those are not the only periodic functions which are there. And in Fourier series, our goal is to express these functions, periodic functions, as sums of cosines and sines. So that is what we are going to do. So what I will do is that suppose there is a periodic function f of t, okay, such that its periodicity is 2 pi, which means that it repeats itself after every 2 pi seconds or hours or minutes. So its periodicity is 2 pi, or its period is 2 pi. Then I can express f of t as a constant plus a series of sums of cosine functions and sine functions. Excuse me, this should be t. Okay. So what you have here is a cosine function, and there are infinite number of cosine functions, and each cosine function has a coefficient a n. Similarly, each sine function has a coefficient b n, and n can change from 1 to 2 to 3 to, and it can go until infinity. So this is the form in which I want to bring my ft to. So this is my ft, and I want to convert it into this form. That is my goal. So the form is already there. If I can figure out what are the values of a naught, a n and b n, then I have my that transformation is complete. So we will figure out how to calculate the values of a naught, a n and b n. So to calculate a0, what do we do? For a0, what do we do? We multiply both sides. So let's call this equation 1. So multiply both sides of equation 1 with dx or dt and integrate it between minus pi to pi, which is the limits of the which is the period of the system. So this is what I will do: minus pi to pi ft dt equals minus pi to pi a naught plus a n cosine nx plus b n sine nt. Excuse me, I am somehow stuck with x cosine of nt dt. So if I have to calculate for this thing, all what I am doing is I am multiplying both sides of this equation by this term dt and integrating the whole equation in the limits minus to pi, which correspond to the period of this repetitive function. So this tells me that because of this I get a0 into 2 pi plus integral of minus pi to pi a n sine nt divided by n minus b n cosine nt divided by n. And actually when I integrate it, I have already integrated it, so I have removed the symbol of integration, and I am going to calculate these limits in the interval minus pi to pi. Okay. So when I calculate the value of this thing in the limits minus pi to pi, sine when t is pi, and n is always a integer, this term is always 0, and when t is pi or minus pi, it's an even function, so when I take the difference, this is always 0. So a0 equals 1 over 2 pi integral of minus pi to pi ft dt. This is one. Next, we will compute the value of an. So an equals what? So here what we do is we multiply equation 1 by cosine of nx and integrate over the limits. So what I get is minus pi to pi ft times cosine, again this should have been time cosine of nt dt equals integral of minus pi to pi a0 cosine of, oh, actually this should not be nt, it should be mt, cosine of plus summation of n equal 1 to infinity an cosine of m nt times cos of mt plus bn sin nt times cos of mt, and then I multiplied this whole thing by dt and I integrate it. Yeah, this is cosine mt, and this should be also, you're right, this is cosine of mt. Okay, so what I get is when I integrate cosine of mt, this first term, and then I take the limits in minus pi to pi, I get 0, and then I integrate, I separate these two terms, and then an, now this is cosine nt times cosine mt, and cosine a times cosine b is cosine a plus b, the whole thing divided by 2, plus cosine a minus b, the whole thing divided by 2. So it is an over 2 cosine m plus n t plus cosine of m minus n, actually should not matter, but I will just write it n minus m t, and this whole thing is being summed from n is equal to 0 to infinity dt plus integral of minus pi to pi bn over 2 n is equal to 1 to infinity, and sin nt times cosine of mt is sine of n plus m t plus sine of n minus m t dt. Okay. Now, if I integrate this term cosine m plus nt, I will get sine, and in the denominator I will get m plus n, and sine when t is equal to pi and m and n are integers, this will be 0, and also when t is equal to minus pi, so this value will be 0. Okay, we will not talk about this right now. Then let's look at this sine n plus mt. When I integrate it, I'll get negative of cosine, and in the denominator I'll get n plus m, and cosine is an even function, so its value will be, whether t is pi or minus pi, it will be same. So when I take the difference, this will be 0, and for the same reason this is also going to be 0. So what I end up getting is an over 2 summation n equals 1 to infinity, and this is sine n minus m over n minus m. Okay, and I can take this value at minus pi to pi, and there is a t here. So t here. Now the value of this is equal to 0 when n is not equal to m. When n is not equal to m, then n minus m is a non-zero thing. When t is pi, then sine of anything times pi is 0, right? And then this is equal to an over 2 times 2 pi when n is equal to m. What happens when n is equal to m? As t becomes pi, and when n is equal to m, the numerator is 0, the denominator is 0, so I have to take the limits of numerator and denominator, and I'll get the ratio. So and what I get is that if I use this L'Hopital's rule, then I get this thing as 2 pi. So my an is equal to, so this 2 goes away, 1 over pi minus pi to pi ft cosine of nt dt. That's the value of an. Okay, so that covers the topic for this particular class. We will continue this particular topic in the next class also, and what we will do in the next class is we'll finish this Fourier series by computing the value of bn, and then we will make this thing more general in context of if the limits are not minus pi to pi but rather from some time period t. So that is what we are going to do. So thanks a lot for listening to this lecture, and look forward to seeing you tomorrow. Thank you.